Ever given a thought to what would happen if momentum was not conserved? Momentum, that captivating concept in physics, is essentially the product of an object's mass and velocity. It's a fundamental principle that governs the motion of objects, from the smallest particles to the largest celestial bodies. Now, imagine a universe where this principle is violated, where the total momentum doesn't remain constant. Sounds intriguing, doesn't it? Join us as we delve into the fascinating world of physics and unravel the consequences of a world without momentum conservation. Imagine the scene of two cars colliding head-on. Now, in our world, the principle of conservation of momentum is at work. This principle, a cornerstone of physics, dictates that the total momentum of an isolated system, in this case our two cars, remains constant unless acted upon by external forces. So what does this mean? Well, let's break it down. Momentum, as you may know, is the product of an object's mass and its velocity. When these two cars collide, they exert forces on each other. According to Newton's third law, these forces are equal and opposite. The force one car exerts on the other leads to an equal and opposite change in their momenta. The momentum lost by one car is gained by the other, ensuring that the total momentum of the system remains constant. That's conservation of momentum in action. But let's indulge in a bit of scientific whimsy. What if momentum was not conserved? In this alternate reality, the total momentum of our two cars could change during the collision. One car might slow down more than it should, while the other speeds up more than expected. The forces they exert on each other would no longer lead to equal and opposite changes in their momenta. The predictability we rely on in physics would be thrown out the window. Now, this might sound like a minor change, but it would have major consequences. The outcomes of collisions, whether between cars, billiard balls, or particles in a particle accelerator, would become unpredictable. The laws of physics, as we know them, would be turned on their heads. The world would become a much more chaotic place, with the outcomes of basic physical interactions becoming anyone's guess. Thus, in a world where momentum is not conserved, the outcomes of collisions would be unpredictable and chaotic. Ever wondered how spacecraft maintain their course in the vast expanse of space? Well, the answer lies in the principle of momentum conservation. Spacecraft, like any other object, possess momentum, the product of their mass and velocity. In the void of space, there are no external forces acting on the spacecraft. As per the law of conservation of momentum, the total momentum of this isolated system, our spacecraft, must remain constant. Now let's consider a scenario where the conservation of momentum does not hold. What happens to our spacecraft? If momentum were not conserved, the spacecraft's acceleration would be affected by external forces, like gravity. The spacecraft might veer off its intended course, or worse, not move at all. However, in reality, this is not the case. The principle of conservation of momentum ensures that the spacecraft's momentum remains constant. This constancy allows scientists to make precise calculations for space missions. These calculations are critical for adjusting the spacecraft's orbit and rendezvousing with other celestial bodies. Think about the precision required for a spacecraft to land on another planet or dock with the International Space Station. Just a slight deviation in momentum could result in a mission failure. Sounds intense, doesn't it? Yet, thanks to the conservation of momentum, these complex maneuvers are made possible. It's fascinating, isn't it? The same principle that explains why a ball thrown in the air eventually falls back to the ground also guides our explorations in the seemingly infinite cosmos. So the next time you look up at the sky and see a speck of light moving steadily across the night sky, remember, it's not just a marvel of human engineering, but also a testament to the fundamental laws of physics that govern our universe. Without the conservation of momentum, our ventures into space would be fraught with uncertainties. At the subatomic level, the rules of the game change, but momentum conservation still holds sway. Now let's delve into the fascinating world of particle physics, where the principle of momentum conservation plays a pivotal role. In this realm, we're dealing with particles so tiny and elusive that they make a grain of sand seem colossal. Here in the strange and wonderful world of the subatomic, particles such as protons, neutrons, electrons, and even more exotic ones like quarks and leptons all abide by the laws of momentum conservation. Consider particle accelerators. Massive machines like the Large Hadron Collider. These accelerators smash particles together at nearly the speed of light. The energy of these collisions is so great that it can create new particles. The behavior of these particles, their trajectories, their speeds, their very existence, all are governed by the principle of momentum conservation. In fact, it's thanks to momentum conservation that we can predict the outcomes of these high-energy collisions. We can tell what particles should be created, and in what amounts. We can calculate their expected directions of travel and their speeds. And when the actual results match our predictions, it bolsters our confidence in the theories that underpin particle physics. One of the most groundbreaking discoveries in recent years, the Higgs boson, was made possible by the principle of momentum conservation. The elusive God particle was found in the aftermath of particle collisions, its existence inferred from the momentum of the particles it decayed into. Without momentum conservation, the hunt for the Higgs boson would have been like trying to find a needle in a haystack blindfolded. So, you see, momentum conservation is not just a principle or a rule. It's a fundamental aspect of our universe, from the cars on our roads to the particles in our atoms. It's a cornerstone of physics that allows us to make sense of the world around us and the world within us. Without the conservation of momentum, our understanding of the subatomic world would be drastically different. It's a simple statement, but it holds a universe of meaning. Remember, next time you marvel at the complexities of particle physics, it's all underpinned by the humble principle of momentum conservation. The principle of momentum conservation isn't just for physicists, it's part of our everyday lives. Indeed, momentum conservation has a starring role in our daily routines. Consider, for instance, the simple act of jumping off a diving board into a pool. As you leap upwards, your body carries a certain amount of upward momentum. Upon hitting the water, however, your momentum decreases dramatically. But have you ever wondered what happens to that lost momentum? Well, it's not lost at all. It's transferred to the water, causing it to recoil slightly downward. The total momentum, the sum of your momentum and the water's momentum, remains constant before and after the jump. This is a perfect illustration of the conservation of momentum in action. Or take another everyday example, walking. When you walk, you're not just strolling along, you're engaging in a constant exchange of momentum with the earth. As your leg muscles push against the ground pushes back with an equal and opposite force. This allows you to move forward. This might seem simple, but it's actually a complex dance of momentum conservation. The same principle applies when you throw a ball, ride a bicycle, or even when you sit down on a chair. In each case, momentum is conserved, ensuring a predictable outcome. If momentum were not conserved, these everyday actions would be far less predictable and much more chaotic. Momentum conservation is a fundamental law of nature. It's not just a dry theory confined to physics textbooks. It's a living, breathing principle that governs our day-to-day lives, allowing us to navigate the world with confidence and predictability. So, you see, even in our day-to-day activities, momentum conservation plays a crucial role. The principle of momentum conservation is fundamental to our understanding of the physical world. From the microcosm of particle physics to the macrocosm of space exploration,